All right, I'm hoping you guys can see everything okay, and hope you guys can hear me as well. And we're just gonna jump right into these reactions. So we talked about, last class, or I guess before exam 3, the ways that we can rationalize radical stability. And the ways that we rationalize radical stability is the exact same as carbocation stability. Okay, so, those features that we saw before, such as induction, is a destabilizing feature. But features like, electron donation via resonance, maybe there's a heteroatom located next door, any of those things would stabilize, these radicals. We also mentioned something called bond dissociation enthalpy, and it just is basically the enthalpy or the heat required to do something called homolytic cleavage. And what homolytic cleavage is it's the, separation of, this bond such that each fragment that results from this original molecule retains an electron. So, that looks something like this. So the difference, what we've seen, is when we see, let's, for instance, let me do this. So we have a carbocation maybe, and we have bromide. Okay, so, both of these electrons, or I'm sorry, maybe I should do this first. I skipped a step. So let me show you this example. So this was, just hydrohalogenation like we saw before. And notice that all the electrons came, attacked this hydrogen, and then these electrons, both of them, all two of them, stayed on the bromine. Okay, so this is heterolytic cleavage. Heterolytic cleavage. And what we mean by heterolytic means that both of these electrons retained on one species instead of, one electron being on one and the other electron being on another. Okay, so the resulting structure would be something that looks like this, and we generate this bromide. So, maybe I'll just circle that. That's the electrons that retained on it. But, when we're dealing with radicals, if I did something like this, and we'll talk specifically about what I mean here in this step, these are the mechanistic arrows that we get, such that each bromine gets one of the electrons. So this is homolytic cleavage. So this is the first time we've seen this, homolytic cleavage. Okay, so that's the difference between the two types of reactions. And, this is the only time, in organic, and at least at your level, that you guys are going to encounter homolytic reactions. Okay, so everything else pretty much, and even in Orgo 2, is going to be, these types of reactions. This is the one example that we're going to do, chapter 8, I guess, in this workbook is. So now that's a little bit of an intro into like what these radical stuff is. Let's talk about bromination versus chlorination. So the first reaction we're going to talk about is you can just take a regular alkane starting material, okay, take a halogen and take some sort of heat or light source and, throw them all together. Okay, so for instance, let's take this molecule. Okay, and let's do Br2 and light. Okay, so H nu is abbreviated as light. It stands for photon. Okay, and what happens is there's something called an initiation step, a propagation step, and a termination step. Okay, so before I even do this, let's kind of write those out. So initiation, I'll do this really quickly. Initiation involved Br2 and light. And these are going to be my two products. So two of the same product is what we generate. How does that happen? Well, this is essentially what it is. So this bromine, and let me draw this accurately, and this bromine, okay, they have massive, massive electron clouds with them because they're halogens with a lot of electrons. And what the situation is that since all these electrons are here, they're repulsive. Okay, so these bromines don't like to be together, which makes this bond really long and actually a really weak. Okay, can you guys rationalize that? A weak bond. You guys see how that would be weak? Because these electrons that are in here and these electrons in here are kind of repelling away from each other like a magnet, which kind of elongates this bond and it makes it weaker. So we have a very low, what we call bond dissociation enthalpy. Okay, so you can kind of rationalize why that. So literally light, just by putting it subject to some sort of radiation, is enough energy to just break that bond homolytically. So the initiation, mechanistic arrows would be these hook arrows. Oops, that's not going to work. And you get two of these bromine radicals. Okay, so that's homolytic cleavage. And also, just something to note is that we use fish hook arrows. What do you mean by fish hook arrows? Before we were doing full mechanistic arrows, like something like this, where there's two heads. For radical reactions, we only draw half arrows to indicate that it's only one electron moving. Okay, so that's actually, it looks like it's not a big deal, but it is a big deal. So that's your initiation step. Okay, that's step one. Okay, so now propagation. Okay, so the propagation reaction is taking your now starting material. So let's say it's this alkane, okay, and I'll draw in, let's just say it's this bond, okay? And, I'm going to take one of those radicals that I generated from that, initial initiation step, and I'm going to show these half arrows as such, okay? So what happens is that one electron in this carbon-hydrogen bond is going to combine in air with this one single electron in this bromine, and then that other electron that was left in that CH bond stays on that tertiary carbon on that center starting material. So the resulting structure is going to be this tertiary radical, okay, and this HBr compound now. So we generated a little bit of hydrobromic acid. Okay, and something interesting about that is this radical right here we want to talk about is that it's sp2, which means that it's planar, okay, which means that it's 120 degrees. And so I guess you could draw that same reaction that I like to, that same nada projection that I like to draw, okay. Okay, and that's the singular electron, okay, and that's the unhybridized p orbital, an unhybridized p orbital. Okay, so that's an sp2 planar 120-degree electron unhybridized p orbital. That's why you can see how carbocation stability is going to parallel radical stability. Anyway, so we're not done. So initiation is always one step, but propagation is always at least 2 or more. So that's step 1. So step 2 is we can take this radical, take more of our starting material. Remember, we always assume excess starting material, and we can keep going. Okay, and the result is a structure that looks like that, and we have now a bromine at that position. Okay, and then we generated another bromide radical. So this is good for our product, okay, for 2, but then we need to do the last step, which is termination. So termination is going to involve, and you can do one of 3 things for this step. You can show bromine reacting with another bromine coming together in thin air to form Br2. You can show, this plus that maybe coming together. I'm sorry, not that. You can do this and that. So, this is just plain starting material. I didn't mean to put a radical there. And then with one of the radicals, you can form, that, and then you can generate another radical or something like that. So that's a way to terminate that guy. That was this starting, that's terminating that guy. Or you can show, I think, a mixture of the 2. You can show this guy and HBr. Okay. To be completely transparent with you guys, I always use this one. It is the easiest one. You get full points every time. There's no reason why to not pick that one, okay? It's just the 2 halogens coming together, termination. Because you only need to draw 1. So essentially, this whole reaction, this whole bromination reaction is 4 steps, okay? So it's initiation, 2 propagation steps, and 1 termination event. Okay, so you need 4 separate steps for that mechanism. Okay, so I hope that was like a good kind of review of where we should be right now, okay, in terms of halogenating these alkane starting materials. Does anybody have any questions so far? Like bond associated, fishhook arrows, how to rationalize what radicals look like, anything like that? Great. Okay, so I'm going to move on to the difference between bromination and chlorination. Okay, so there's a difference. So let's take that same starting material that we just talked about. Maybe let's take this, and let's do 2 different things. Let's talk about these carbon hydrogens bonds over here. Okay. And there's something different about this one. Okay, so if I were to classify, these carbon hydrogen atoms, okay, they would be primary carbon hydrogen atoms, okay, or primary carbon hydrogen bonds. So I'm going to call them primary CHs. I don't know. That's just how I want to call them. And maybe those green things, these are tertiary CHs. So let me call that tertiary CH. So how many primary CHs do I see? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's 9. So let's just put a 9 maybe here. And then when we see how many tertiaries, there's only 1. Okay, so 9 out of a total of 10 means 90%. And 1 out of a total of 10 equals 10%. So just keep that in mind. Okay, so if I want to, maybe subject this to bromination conditions, I should expect that 90% of my products look like that. And, maybe 10% of my products look like that, purely just based on statistics and how many hydrogens are available. We talked about homolytic cleavage and the fact that all these CH bonds are really, really weak. Okay, these CH bonds are relatively weak, so they can come off. And the only thing that we're talking about here is the difference in substitution. There's 9 primary hydrogens, and then there's 1 tertiary hydrogen. So based on just statistics, you should get 90% of these primary bromines on here and 10% of these tertiary bromines on here. But what is reality? Okay, reality is not matching our expectations here. And in actuality, we have of that same guy 0%, and we have actually almost exclusively 100% of that more substitute starting material. So that is really mind-boggling. Why do we form 100% of this starting material when, it says that statistics shouldn't be like that? Okay, so that's weird. So keep that in mind. Let me compare the chlorination conditions as well and see maybe what's going on there. So I want to take this, same material. Maybe I'll just substitute it for chlorine instead of the bromine. And then I basically get, this alkane, okay? Or I get this one. So we get the same. We have the same expectations. We expect 90% right here. We also expect 10% here. But in reality, we get 62% and we get 38% this guy, okay? That's weird. So now it looks like for the chlorine conditions, we get almost like a definitive mixture, a more certain mixture of these products, whereas bromination is exclusively that more substituted material. So maybe that should give us some insights into knowing that bromination is regioselective. Chlorination is not, okay? So let's write that, I guess, in huge words. Bromination is regioselective. Chlorination is not, okay? That's like the biggest takeaway, from, I guess, this chapter is bromination is regioselective and chlorination is not. And we're going to talk about that for why in a second. So, if you look up your periodic table for a second, if you guys have one in front of you, you guys would see that, bromine is lower on the periodic table by, I think, 1 row than chlorine. So I guess if I can draw a little picture here, you can put like a whole bunch of elements and then bromine, yada, 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 down, okay, something like that. Okay, so bromine we know is a little bit lower on the periodic table, more shells, more protons, more electrons, okay? So if I want to do this comparison, let me draw these side by side. Okay, so let's talk about, which one is more stable. So this bromine radical is more stable because we have more protons because it has a higher atomic number, and more protons means more positive charge in the center of this nucleus. So if there's more positive charge at the center of this nucleus, it can stabilize this electron or the singular lone pair. The singular electron in that lone pair, I guess. It makes it more stable. Whereas here, we don't have as many protons to stabilize the electron, so it's relatively unstable. And this is more stable. Okay, so then what about, maybe fluorine and iodine? So those are the 2 other ones that fit right above and below. So fluorine, if you're following this, would be even smaller. So this would be too unstable or too reactive. Okay, and iodine would be a little bit bigger than bromine. So iodine is too stable, where it's too unreactive. Okay, so these don't happen and these don't happen, but bromine and chlorine is this nice kind of intermediate where bromination is a lot stable, so it's very regioselective, and chlorination is not. So does that all make sense for you guys so far? Somebody put something in the chat box just so I know. Say yes, someone. All right, can someone just verify that you guys are all getting this? Awesome, thanks. Okay, cool. So let's just jump into some practice problems real quick. So we're gonna go on to page 93 of the student workbook if you guys are there. You guys are almost done with this book, it's awesome. Okay. So essentially, we have this material, we have the starting material, and we know bromination conditions is going to be regioselective to form a bromine on the more stable, more substitute position. So out of all these positions, we have this primary, tertiary, and then secondary benzylic. So, which one's the best? Well, if you said secondary benzylic, you're totally right. So we're going to go through this radical. Okay, we're going through that kind of benzylic radical, and then you can see how a bromine would come and attach there. So remember, at this point, we go from sp3, okay, to sp2, and then now we're going to go back to sp3. So remember, that has a stereochemical consequence. We lose any stereochemistry that was in this starting material. Then it becomes, planar, no stereochemistry, and then now you have to account for both major stereoisomers. Okay, so we would expect the bromine there, but we generated a chiral center. So we have to consider, that could have approached on the front face of that unhybridized p orbital to generate, this wedged configuration, or it could have came on the back face of that unhybridized p orbital to form this dash configuration. Okay, so these are my two major stereoisomers. And notice it's only this major stereoisomer because we said the bromine radical was more stable and it's regioselective, so we're going to get exclusively 100% of the more substituted products. Okay, we're going to keep going. Okay, so for letter B, we see we have chlorination conditions. So we know chlorination is not regioselective, so we're going to get a mixture of everything. Okay, so let's just try that. So you should have a lot of products for these. So that's our product. Okay, so at this primary position. Okay, well, I could have said it also went to maybe this secondary position. Okay, well, if it also went to that, there's another major stereoisomer at that position, so maybe it's that. It also could have been, at that tertiary position. Again, no chiral center there because it's two ethyl groups. And if I were to move it anywhere else, it would duplicate a structure. So these are my four major structures for that. Okay, so notice that any of these are possible based on, our statistical yields that we saw before. Notice we saw 62% and 38. So who's to say, yeah, it's a little bit less, but, it still exists in solution. So we need to draw all of these. Okay, let's do bromination conditions again for part C. So we see that we have, these primary and secondary carbons, but we have specifically one tertiary position right there. So we would expect, since this is, 4 different substituents, and okay, so those would be the two for here. Just draw this line here. That'd be that guy. And you can tell there'd be a lot of chlorination conditions here. Specifically, you would get a mixture of a lot of cis, trans, geometric isomers. I mean, I'm not going to just spend time to draw these out, but you have one here, one here, one here, 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 here. Basically, every carbon-hydrogen bond you see, you could potentially have a chlorine product. So for the bromination conditions, we have this, I guess you could say quaternary position right here, and that would make you think to put it here, okay, to make you put this, bromine at that position. Is there not plane of symmetry, Farah? Is there not plane of symmetry on part D? D. There would be if you had the chlorine on this position over here, Farah. There would be a plane of symmetry there, yeah. But other than that, there wouldn't be because there's no symmetry. Does that make sense? Okay, yeah. Okay, so you would think to put it on this quaternary position, but remember how many bonds are here? We have this carbon bond, this carbon bond, this carbon bond, and then this carbon bond as well. So, we don't really have any CHs to break. So there's only one, really option here, and it's to break that tertiary position. Do you see that? So then essentially it should be at that position up top. And we could get that there, or we could have got this diastereomer. Okay, and that's that one. So does anybody have any questions on bromination or chlorination in terms of free radical mechanisms? Great. Okay, so we're going to talk about the second to last reaction. So there's only 3 reactions in this chapter, but second to last one. And okay. So actually, I want to just show you one thing real quick. So, real quick, we talked about these radicals and how to generate them. So essentially, we have Br with Br, and we put some sort of heating starting material or heating source, and we get these 2 bromine radicals. But there are other species that can homolytically cleave like this. So one example which we're going to talk about right now are peroxides. So one example I can draw is hydrogen peroxide. So hydrogen peroxide looks like this, and it's Lewis structure. And essentially, this liable oxygen-oxygen bond is extremely, repulsive. It makes the bond really weak, really long, and, I can homolytically cleave that to form 2 hydroxide radicals. Okay, so 2 hydroxyls. So that's one example. But, specifically for my area of research, and I know it's funny, this is why I'm bringing it up, it's because Dr. Habenek put it on her problem set, is I use something called azo-isobutyrylnitrile. I know that's a mouthful. Isobutyrylnitrile, and the abbreviation is AIBN. So if you guys see that, I use this all the time. It's like this white crystal, really, really pretty chemical, but essentially it looks like this. So I think it's worth talking about, since it was talked by Dr. Habenek on her practice exam. So this is the structure, and again, you don't have to memorize this. This would be like given to you on a test. But the reason why we use this is there has a very, very large entropic driving force, and the entropic driving force for this is the fact that these electrons are going to do this. And you guys don't need to do this, but I just want to show you this real quick. Is that you generate these I don't even know what this is. I don't even know the right name for it. It's like bis-utyrylnitrile, like it's radicals. So you have 2 of those. Okay, so you can see that. And you also generate nitrogen gas. Okay. The fact that you generate nitrogen gas and you have 3 molecules. So we went from 1 molecule to 3 molecules. And that is clearly increasing disorder because we have more of something. So we have a huge entropic driving force that promotes this reaction. So this is a great initiator for radical reactions. So we use this all the time in my lab. Just something I thought to say. But anyway, so it doesn't have to be Br2. So we could have these radical species. So these radical species brings us to our next, these peroxide species, and these peroxide species is going to bring us to the next reaction. So essentially, I'm going to go over here, and this is called free radical addition of HBr to alkenes. Okay, so let me just show before, when we did this, we generated carbocation on this position, free bromide, and then bromide could come in and form that structure. Okay, so we formed a Markovnikov product. Okay, and then now let's take that same starting material, subject it to HBr again, but now in the presence of peroxides and heat. So I'm just going to draw maybe ROOR. Okay, so peroxide is just OO. And this R just means like the rest of the molecule. So you can see it as ROOR. You could see H2O2, that's hydrogen peroxide. Anytime you see like these 2 oxygens next to each other, it's a peroxide. Okay, so what's different now, and I'm just going to go right to the product, is you get the anti-Markovnikov product. Okay, so this is the only way we know how to do anti-Markovnikov addition to alkenes. Okay, so in terms of halogen addition, so that's weird. So how does that happen? How does that play out in the mechanism? So let me show this to you guys. Where did I put all that? Okay. So eventually the reaction works like this. So I'm going to take the letter F from the student workbook if you guys are looking, and I'm going to draw it over here. Okay, and we have HBr and things like that. Okay, so I'm going to draw ROOR, and I'm going to draw HBr. So these are our main players going on here. So essentially what's going to happen first is that we're going to have, this heat source. So I'm going to draw it here, 1. We're going to have this heat source, and it's going to homolytically cleave this peroxide. Okay, so 2 of those, essentially. Okay, so then now that is going to react with the other starting material, the other reagent that we have. So let me just pick one of them. And HBr. Essentially what happens is this, peroxy radical is going to extract a proton from hydrobromic acid, generating the bromide radical as the end product, as well as now you just formed an alcohol. You just formed whatever that R chain was and this hydroxyl group, because we abstracted a proton from the hydrobromic acid. So we're there. So that is, our main initiating steps. So now let's bring in that, starting material. So now we're on to propagation. So in propagation, we're going to bring in that alkane, or I'm sorry, this alkene, and that bromide source that we generated from the initiation step. And essentially what happens is, this is the same exact thing that we saw, I guess, back with carbocation stability. We wanted to form the carbocation on the more substituted position, okay? We don't want to form the, we we want to form the carbocation on the more substituted position, which means we also want to put the radical on the more substituted position. So essentially, what these mechanistic arrows are going to be like is this. So notice that one of the electrons in this alkene bond is going to form with this bromine and add this bromine on this secondary position to form this radical on the tertiary position, because it's a more stable radical center because of reasons we talked about, hyperconjugation. See, orgo does not go away, so it's good to understand things. Hyperconjugation, and we formed a bond to, a CBr bond in the less substituted side. So this was the anti-Markovnikov way of adding a halogen in. And then the last step is just a termination step. So I can take, that active bromide center with this radical, and I can take, maybe HBr and show that. And you would have to consider, all major stereoisomers here. Okay, so that'd be 4 total. All right, so that kind of makes sense on that type of reaction. So, before we saw our HBr, with an alkane, regular Markovnikov addition, okay? But the fact that we have this peroxide present, interferes with that, and we have anti-Markovnikov addition, okay? So again, nothing crazier here. I just think noticing that with a peroxide present, it's anti-Markovnikov, you guys will be better. All right, let's jump into some practice. Okay, so for F we just did, so let's just go to G. So which is the more or less substitute position? So this is more, that's less, so clearly the bromine is going to add here. So in terms of predicted products, it's really easy. So we have, maybe we have this bromine here and we have this here. So we generated a chiral center here and a chiral center here. So we would expect, a mixture of those geometric isomers, the cis and the trans ones. So there would be 4 major ones to draw there, okay? For H, again, we have this primary position and then this tertiary position. And, this specifically is called tert-butyl peroxide. TBUO is sometimes it's abbreviated as tert-butyl. It's tert-butyl peroxide. Sometimes you see it like that. Sometimes you see it as toot because it looks like, tert, I don't know, toot, I don't know. So those are all different things that you see. So tert-butyl, terpene oxide, I don't know. So the primary position would be, the position that we'd expect this bromine to add on to. So we're there. Easy, no other stereoisomers. Okay, I. So again, we have, so here we see hydrogen peroxide instead of, tert butoxide or, just ROR. And this is our benzoic position, and this is just a plain secondary. So definitely that plain secondary is what I want to add it onto. So it's here. And then remember, major stereoisomers, we get a wedge and a dash. So, okay. And okay, so this is interesting. Okay. So we would expect that the radical to form on the more substituted position because that's more stable. So that's the secondary position right here. But what does that ketone do? What is that ketone's role kind of in that center? So let's just kind of go with the mechanism and see what would happen. So if I were to put the radical on the more substituted position like I'm supposed to in the mechanism, and I see this carbonyl here, what does that do? Well, it's induction and it's destabilizing, okay? So really, you're not gonna form the radical here, you're gonna form the radical here, okay? Because that's the more stable position. And then, the bromine adds here, okay? So then that leads to, and this is where the CH bond formed, okay? And then this one make more sense. Like, although you thought to put it on the the bromine on the less substituted position, it couldn't this time because the radical that forms there is destabilized with induction with that carbonyl. That makes sense. David, the book says it goes on the right carbon. David, yeah. That's normally what's a thing. I don't agree with that. The key. This is something I definitely want to ask Dr. Peterson about. So David, one of the issues I have is I know radical chemistry a little bit too much. So like, even though this might be true, like this may not be something she expects you to know in the sense of like for your test. She might just go like, oh, just know to put on the less substituted position, even though like this is the real, I guess, kind of picture. So for now, David, just go with the other answer. Everybody else that's watching, go with the other answer. Just go with this then. And I'm just going to get clarification with her. Okay, it lost substitute position. Letter H has serotonin on the methyl group. Letter H. Yes. Oh my God, I didn't even notice that. Yeah, awesome. So David's talking about, this position right here, this H over here. And yeah, so I didn't even notice before it was 2-methyl. I mean, this group's over here. And then because we added the bromine onto it, it became a different substituent. So they missed that. Awesome. So there would be, those two isomers right there. Great job. And could it be on the CBR group? Which one are you talking about? Stereochem? Could it be on the CBR group? Oh, no. You're not going to put any stereochemistry right here. You're not going to do like wedge dash. Okay, you would do it like, what was that? Do you have a question?
From like the CBR group, but like the bond leading to the CBR group. Like coming
so like this guy?
Yeah.
Yeah, you can do that. That works. You can either do it there or you can do it at the methyl there, whatever you want. And then we can draw this guy as well. Okay, so is that good? Awesome. I love when you guys catch me because it means you guys are paying attention. All right, and then the last one I want to talk about, so we have one more reaction to discuss, and that's allylic bromination. So is everybody kind of good on peroxide stuff? I'm just gonna, again, I'll double check and I'll let you guys know next week if this was just too in depth for you guys to know. Okay, so allylic bromination. So in years past, you guys didn't have to know the Lewis structure of N-Bromocetamide, but I guess Dr. Habenex put it in her notes, so I think it's kind of important to know what that looks like. N-Bromocetamide is basically a derivative of, this anhydrous, cyclic structure. So, this is an acid anhydride. You guys have seen that. Okay, so that's acid anhydride. And N-Bromocetamide is a derivative of that. So it's the, amide version of that. And then you have a bromo group coming off. So that's this is the original parent material, this cyclic acid anhydride. And then it turns into, this N-Bromocetamide derivative. Anyway, it's really easy. There's symmetry right here with the carbonyls and the N-bromo bond. So you can tell that there's going to be significant repulsion with the lone pairs on the nitrogen and the lone pairs with the bromine, which makes this bond really, really weak and really, really labile to homolytic cleavage. Okay, so if I wanted to just draw the initiation step without even drawing a main reaction, I know it's going to be something like that. And the result is you're going to form this, cyclic structure that is extensively, not conjugated. You can have a lot of resonance going on here with these, other, groups going on. And you also generate bromine, okay? So that free bromine is our source of radical that we're going to use in these reactions, okay? So NBS is used in allylic bromination, okay? So if we're looking, maybe I'll just do K on the 7-sheet paper. So let's do this. Okay. So NBS, and so essentially whenever you see NBS, just think BR radical. Okay, just think BR radical. And there were 2 allylic positions. Okay, so allylic means 1 carbon removed from an alkene. Okay, so allylic would be, maybe we have, this position right here. Let me circle it in red. Or maybe we have this carbon right here. Okay, so let's draw, a radical on that position. Okay, so the result would be, maybe something like, let me choose this one. I'm doing it on purpose for a reason. Okay, so I'm going to pick that one below. And something you always have to check with allylic bromination is resonance. Okay, and I'm going to get to that on the next page as well. But you need to see if I can move this pi bond anywhere around this structure such that it would become more substituted and more stable. We talked about alkene stability, that the more substitute it has, or the more substituents that there are, the more stable it is. So essentially right here, this is something we've never checked before. This is some sort of I guess it's a version of carbocation rearrangement. I guess you can kind of say that it's radical rearrangement. And what it is essentially the rearrangement would follow the form of that. Okay, so then the pi bond moved there, and now we're there. So was there any difference in substitution of that alkene? No, it went from a disubstitute to a disubstitute. So there's no difference. So again, there was no really reason to do this. So this one doesn't really show any insights. But now let's pick the other allylic position. Maybe I'm gonna pick it here. Okay, so if it's there, okay, can I resonate any such way? Yeah, I can. To get. Oh, okay, so if you guys are having an aha moment, maybe this should make sense. We went from di-substituted to a tri-substituted alkene. So this is the radical that I want to use because an internal rearrangement is possible that makes that alkene more stable and then allows me to add a bromine there. Okay, so the end product is going to be something like that. Cool. Because this radical comes with the bromine radical. So then you go there. So, you know, your main end product of this is going to be wedge and then dash. Okay, awesome. Any questions on that? Okay, so therefore can resonate. If you guys read this up here, this is important, this resonance thing. Okay. So would having a more stable alkene be more important than a more stable halogen? Exactly, yes, that's the most important thing. Yeah. The halogen does not matter in any near capacity than the alkene does in terms of priority. Very good point. All right, so let's keep going. So again, for the cyclic structure, we have, 2 allylic positions. We're talking either, here or here. Okay, so you can clearly see ahead of time, maybe not yet, but I can see ahead of time why this one would be better. Because if I put a radical here, I can resonate with this pi bond to put the pi bond on the tri-substituted position instead of the di-substituted position. Do you see that? So maybe if you didn't, I'm just going to draw those steps real quick. Here would be the best radical to start with. Okay, because internal rearrangements are possible to get. This tri-substitute alkene again, and then the bromine just comes on there. So we have this, that, and ethyl group. Oops, I forgot that ethyl group. And then we can have this bromine there. Then we get, I know I'm getting all sloppy over here. And then that guy. Okay, so those 2 diastereomers. Okay. Again, same exact situation. So in this case, it's easy. We only have 1 allylic position, so it's here. So yes, I see an internal rearrangement possible. So I'm going to go right to this structure, and then you can see maybe faster how I got here. Okay. So if you didn't see that as quick as that, maybe I'm trying to get faster so you guys can see this. That's the 1 allylic position. Resonate, resonate, resonate. So then you get that, and then the bromine just attaches on. Okay, so again, we have multiple allylic positions here, here, and here. Clearly, this one is going to be better, this one on the right, because we can form I guess it's tri-substituted again. So that leaves these structures. Okay, and O, I'm going to give you guys a second to look at it. You guys see we have an allylic position here. We have an allylic position here. Okay, since there's symmetry, it doesn't matter. But you can see that by resonating with that position, you're going to get a tri-substituted alkene. So we're there. And then you can add the bromine right here. And then do the same thing. Cool. All right. And that's it. So last thing I want to talk about real quick is so if you guys didn't understand what I was talking about with the resonance stuff, here it is. So provided below are these 6 allylic radicals already. Okay, so that's kind of, the first thing that I did before on this last page was, just kind of fold this over, was, draw the radical on all these, this is what I meant by the red circles. Draw all these radicals at first, and then see if resonance can happen. So this would be equivalent to me drawing all those radicals first. So which ones are not already in the most stable position? Okay, so let's just think about that. If I were to resonate, maybe this pi bond out and that in there, I went from a tri-substitute alkene to it looks like a di-substitute alkene. So no, this is fine the way that it is. I don't want to resonate anymore. It's good the way that it is. So no, A is not one of them. B, okay, so clearly right now we have a di-substituted, this geminal, alkene. And if I were to resonate, maybe, oh, it becomes tri-substituted. Oh yeah, that's definitely good. If I resonate, I can get a more stable alkene in the ring, tri-substituted. Yes, B should definitely rearrange. It's not in the proper resonance structure right now. Right, again, over here, you have a secondary geminal, a di-substituted geminal again. And if I were to, resonate here, and here, and here. Oh yeah, I definitely went to a, wow, I think it's a tetra substituted. So yeah, that is definitely in need of a rearrangement. D, right now I'm di substituted, but I can tell already if I move to the left, it's going to be mono substituted. So no, that's not that one. E, right now again, this pi bond unfortunately is too far away for it to participate in allylic bromination, but this one could. So again, this is a geminal, I guess you could say, di-substituted alkene, and if I were to resonate inward, you would get tri-substituted. So E is definitely capable of rearranging. And then for F, you're already in this kind of tri-substituted format. But if I were to resonate, to the right over here, I get tetra-substituted. So those four definitely could rearrange. Okay, so I think that was pretty easy. And then I'm going to leave 9, A, and B for you guys to do on your own. So you guys can just draw those full mechanisms out, practice with those, check yourself with the key. And let's talk about 10 real quick. So that was literally all of radicals. Radicals is a really short chapter. It's important, but it's really, really short and intuitive. Okay, so 10. So sometimes you might get these reaction coordinate diagrams, especially for radicals. We like to do that for them. But essentially, the reaction coordinate diagram for the two propagation steps of the free radical bromination reaction, so it's just literally Br2, heat, and toluene, okay, is shown below. And this is the reaction coordinate diagram. So draw the structures that correspond to point A. Okay, so let's just draw the mechanism and see what they're talking about, because I have no idea what that means. So maybe I have toluene, and I'm just going to draw a hydrogen bond in there, and I have bromine, and I know it's going to do with the heat to get 2 bromides. So I know I'm here. Okay, so if I'm here and the first reaction is abstracting. So again, this is the reaction coordinate diagram for propagation steps. Okay, so none of this initiation is on this chart. So don't even think about that yet. So we have these two things because that's initiation. Okay, so then propagation is going to be when this bromine, now this is the first step of propagation. Oh, well, I would just say the first step of propagation is that bromine radical coming and abstracting a proton. Okay, so the result could be, so you have this, and you might have that. Okay, so those are the 3 things that I have at step 1, or this position, intermediate in point A. Okay, we have this toluene benzylic radical, we have the HBr that formed from that, and maybe excess, radical that we had from the beginning. So those are the 3 things that I would draw. For B, draw the structures that correspond to point B. So that's just literally the end of the propagation. So for part B, that would just be this bromine radical coming with that toluene radical. Okay, so coming together, and we maybe have that with a BR attached to it. And there's one more, and you could also argue, I don't really know what the are there 2 structures? There's no stereochem here. I would assume that, I guess, that the other one would just be just this. Someone check the key and verify if that's another structure for B. I'm kind of drawing a blank on what I think the second one would be. For B, you react with a molecule with Br2 instead of Br. Ah, thank you. Okay, so yeah, that's awesome. I was drawing a blank and I was like, why am I not getting this one? So yeah, it's not this bromine radical. Sorry, thank you. It's Br. Totally, I really appreciate. That's actually a big common mistake, and I just fell into that. It's a common mistake on these exams. People like to use the Br radical, but it's a whole fresh source of bromine that comes in. Okay, so thank you for that. I really appreciate it. So it's that, and then by proxy, that. Okay, thank you. I appreciate it. Okay, and see which transition state is encountered during the rate determining step. Okay, so you didn't have to know anything about this, but clearly TS1, because that is the longest or the most amount of energy. Okay, and then D, if chlorine were used as a reagent, how many unique products would you get? Okay, so we know D is going to be not regioselective. So we had this position 1, 2, 3, 4, 5, 6. Okay, so that you get 6 products, but how many of them are unique? Okay, so that's the key. How many are unique? So we have 1, okay, 2, any of those would be equivalent, 3 or 4. So that's 4 unique products. Okay, does that include stereoisomers? I don't know if she meant include Dr. Peterson meant to include if that meant stereoisomers, but okay, if there are 4 main structural products pending the stereoisomer argument. Okay, so yeah, that's pretty, as much as I guess you would expect for a critical thinking problem on these. I'm gonna leave the rest for you guys, and we're gonna pick up with chapter 9 material next class on Monday. Chapter 9 is tough, I'm gonna be honest. Chapter 9 is like the toughest chapter for like all of Orgo 1. So if you're good on chapter 8, that's good. Chapter 10 and 11 are also really easy, but just know that chapter 9 is definitely gonna, or at least section 9 in my book is definitely the harder chapter. So just prepare yourself for that. And if you guys have any other questions, I'll hang out for a few more minutes and put in the chat box, and I'll hop on the other computer.